Now let us move on to the PhD interview questions. Let's start with the condensed matter physics questions. So these are the questions that have been actually asked to me as well as my friends in IITs and IISER PhD interviews, as well as to the seniors whom I have connected with. Kindly give importance to these questions. First one is my favorite one. So this question is asked to me in IISC. The question is like this. So one professor from the panel, he told me to write the EK diagram, band diagram of a direct bandgap semiconductor. As you all know, it look like this. Energy K is actually momentum. K is wave vector, but it actually represents momentum. So EK diagram looks like this. Here it is valence band, and the conduction band looks like this. You have to be careful that the minima of the conduction band as well as a maxima of the valence band should lie at the same line. And now he asked me, where do the electron lie in the valence band? Suppose if there is an electron in the valence band, where do it lie? The meaning is that, does it lie in this area, in this area, or it lies only in this curve? The answer is that the electron can only lie in this curve. It cannot lie in this area. Okay, so keep it in mind. Now he told me to consider an electron at the valence band. So as I have already said, electron can only lie in this curve. So I drew a point at this particular position. Then he told me that we are switching on the light. Light is getting incident on this electron. So we have to draw it like this. So the questions will be like this. It will start from a particular question and then it will move on to the next question. So it progresses slowly. It becomes it begins with an easy question and it becomes slightly harder as we go on. So the radiation will be like this. So, and then when he told me what happens to the electron, I said that the electron will get excited and move to conduction band. Then he told me that I should ask what is the energy of photon, but I didn't ask that. So that was my mistake. He told me that only if the energy of the photon is greater than the band gap, then only electron can go to conduction band. So I should ask that. So you should ask that, okay? So this is how the transition will take place. Then he asked me to conserve the energy as well as momentum, to write the conservation laws for energy as well as momentum. Now, as we can see here, suppose the initial energy of the electron is A1 and final energy is E2. So you have to draw these things in the board, okay, on the board, okay. Now, if the initial energy of electron is E1 and h nu is the energy of photon, it gives E2, final energy. So energy conservation is okay, no issues. Now comes the problem, momentum conservation. We know that we have a concept, we have a preconceived notion that when electron moves from valence band to conduction band for a direct bandgap semiconductor, momentum does not change. Actually, it is like that in all the textbooks. So it lies in the same line. So K is not changing. So momentum is not changing. So if it is true, if what I said now is true, then suppose P1 is the initial momentum of electron. Then there will be some momentum of photon, right? Let's take it as momentum of photon. Giving P1, right? Because momentum K is not changing. Electron is moving from here to here, but K is same, right? So momentum is not changing. P1 plus momentum of photon is, the final momentum is also P1. So momentum is not getting conserved. Where does the momentum of photon goes? He asked that. So when I wrote like this, so energy, it is simple, it is okay. And when I wrote momentum like this, then I also get confused. So where does this momentum of photon goes? So then they will give hints, okay? If you get struck anywhere, they will give hints. He told me to think with respect to the values of momentum. Then you have to carefully observe what hints they are giving and think from that point of view. Let us evaluate the momentum of electron. We know the momentum's formula is P is equal to square root of 2mE, where E is energy. Here, the band gap's energy is of the order of electron volt. As you know, for silicon, it is 1.1 electron volt. For germanium, it is 0.7 electron volt. So the order of energy here is electron volt. So we can take the energy of electron to be 1 electron volt for just estimation. Here just the order of value is enough. So square root of 2 into mass of electron is 9.1 into 10 raised to minus 31 into energy. 1 electron volt is 1.6 into 10 raised to minus 19 joule. Now we can write 9.1 into 10 raised to minus 31 as approximately 10 raised to minus 30. And 2 into 1.6 is approximately 3. So square root of 3 into 10 raised to minus 49. This is approximately equal to 10 raised to minus 24 or 10 raised to 20, minus 25, because 10 raised to minus square root of 10 raised to minus 49 is 10 raised to minus 49 by 2, which comes near 10 raised to minus 24 or 10 raised to minus 25. So the momentum of the electron is of the order of 10 raised to minus 24 or 10 raised to minus 25. Now, let's estimate the momentum of photon. Momentum is given by E by C for photon. E is the energy of photon. Also, we are taking it to be 1 electron volt. 1.6 into 10 raised to minus 19 joule by velocity of light is 3 into 10 raised to 8 meter per second. 1.6 by 3 can be written as 1 by 2, because 1.5 into 2 is 3, so we can approximately write it to be 1 by 2. So 1 by 2 into 10 raised to minus 19 by 8, right? So 10 raised to minus 19 minus 8, so 10 raised to minus 27. So the order of momentum of photon is approximately 10 raised to minus 27. Now compare the order of value of momentum of electron as well as photon. The momentum of electron is about 1,000 times greater than the momentum of photon. So when compared to the relative to momentum of electron, the momentum of photon is negligible. We can neglect it. So that's how we can write the conservation law for momentum of electron getting excited from valence band to conduction band. Actually, the K value is getting changed. If you see minutely, the K value is getting changed, but the value is negligible. So we can write it to be like this: momentum initial plus momentum of photon giving momentum final. As momentum of photon is negligible when compared to the momentum of electron, we can write momentum of initial momentum to be approximately equal to final momentum. Hence, it will be advantageous for you if you know the order of magnitudes of certain physical quantities. So I'm giving some values that will be useful for interviews. So here band gap for insulated is greater than 2 electron volt. Semiconductors, metal and superconductor, it is of the order of 1 milli electron volt. And this corresponds to the electromagnetic spectrum, ultraviolet, visible, infrared rays, their corresponding wavelengths. So it is not necessary to mug up the entire wavelength of an electromagnetic spectrum, but at least study for ultraviolet, visible and infrared rays. And these are the wave number of rotational spectra, vibrational spectra, electronic spectra, the wave number required for molecular dissociation. Then the next one is conductivity. This is very important. You have to know the order of magnitudes of typical conductivities of conductor and semiconductor, insulator and superconductor. Then these are also some values you have to remember. Energy of copper pair is 10 raised to minus 3 electron volt. And typical mobility of free electrons is also 10 raised to minus 3 meter square per volt second. I have written for you to remember it easily. Mobility starts with the letter M. If you rotate it, you will get 3. So 10 raised to minus 3 meter square per volt second. And typical relaxation time can be typical relaxation time of free electron can be found out by this equation: mobility is E tau by M, and from this tau is equal to mass into mobility by electron. Typical mobility, plug it in, you will get the typical value of relaxation time. Order of magnitude of binding energy per nucleon is 10 mega electron volt. So this question, order of magnitude of binding energy per nucleon, this has been asked to me during the interviews, even though it is completely unrelated. I'm faced with such questions, so that's why I'm giving you here this particular value. And for resonance particle, the lifetime is 10 raised to minus 23 second. And thermal voltage is given by kT by E, where K is Boltzmann constant, and room temperature is 26 millivolt. Now let us move on to the second question. So this was the question that was asked to me in IISER Trivandrum. The first question they asked is to draw the structure of graphene. So the structure of graphene is something like this. It looks like hexagonal structure. So this is the structure of graphene. These are the lattice points. These corners are the lattice points. When I drew the structure of the graphene, they asked me the second question. They asked me whether it is a valid lattice or not. Is it a valid lattice? So I got confused. So they gave me the hint saying that I have to think with respect to the definition of lattice. So what is a lattice? We know that lattice is a mathematical space in which the atoms or molecules or anything are represented as points in space for which the environment of one point is exactly identical to the environment of all other points. All points in a valid lattice have identical environment. So that is the important part you have to highlight in the definition of lattice. So let's check here. Is it identical? Is the environment of all points identical? Let's see this point. If you are considering this point at a particular distance north of this point, say this distance, let it be A. There is another point. Let us consider the nearby point as well. So here also at A distance, there is a point north of this point, and at some degree left of this point, there is another point, right? But to this point, at some degree to the left of this point, there is no atom or there is no point, and there is no lattice point here. So the environment of this point and this point is different. So it is not a valid lattice. Why? Why not? Because the lattice points present in the structure of graphene, the nearby lattice points have different environment. Their environment is their surrounding are not identical with respect to each other. So it is not a valid lattice. Then they asked me how to make it a valid lattice. As I have said that it is not a valid lattice, then how can we make it a valid lattice? The answer is like this. To make it a valid lattice, we have to consider the lattice points present in the graphene structure to be composed of two sublattices, in which one sublattice contains points such as this one and the alternate ones like this. This forms one sublattice. Let's say the red one as A, and other one is this one. So this is B. Now when we are only considering the A sublattice, these points, then it is a valid lattice. Let's check that. So if we are considering this point, at some distance north of this point, there is one point. So when we consider this point also, at some distance north of this point, there lies another point. And at some distance left of A, there is another point. Similarly, to this point also, at some distance left, there is another point. And for this point, at some distance right, there is this point. Also similarly, and for this point, at some distance right of this point, there lies another point. So now for all points included in the A sublattice, the environment is identical. Similarly, for B all points have similar identical environment. Now it can be made. So now it can be considered to be a valid lattice. So the answer is that if you are considering the lattice of graphene to be composed of two sublattices, A sublattice and B sublattice like this, then it can be considered as a valid lattice. So it is hexagonal in nature. It belongs to hexagonal crystal structure. So we know that there are 14 provides lattice which can be included in 7 crystal systems. So this belongs to hexagonal crystal system. Now they asked another question. Now they asked me to draw the primitive unit cell of this lattice. We know that the unit cell is the building block of a lattice. It is the smallest repeating unit. So here we can draw it like this. So this is the primitive unit cell of the lattice. So next question they asked was how many atoms are present within a primitive unit cell. Here we can see that in these corner points, all these corner points contribute one atom, and there is an atom inside the unit cell. So there are 2 atoms per primitive unit cell. Then they asked me to draw the reciprocal lattice of graphene lattice. So I have drawn the A sublattice only. I have considered only A sublattice. Then this is the primitive unit cell, as I have already told you. And the primitive translation vectors, primitive lattice vectors are A and B. And we know that how to find the reciprocal lattice vectors. If A, B are the direct lattice vectors, then the reciprocal lattice vectors can be found out using the formula A star is equal to 2 pi into B cross C by A dot B cross C. But here we don't have C. Here we are only considering the uni lattice. So the C vector can be taken as Z cap. So we don't need to do this calculation, as we don't have the value or along x direction, along y direction. We just need to we know that A star will be perpendicular to B. Similarly, B star will be perpendicular to A. So drawing A star, as A star is perpendicular to B, we can draw it like this. And as B star is perpendicular to A, we can draw it like this. So the unit cell in the reciprocal lattice will look like this, something like this. So drawing it separately, we will get like this. So this is the primitive unit cell in the reciprocal space. Now we can fill in the lattice points like this. Now they told me to draw the Wigner-Seeds unit cell. To draw the Wigner-Seeds cell, we know that we have to draw lines from a lattice point to all the nearby lattice points. So here it is like this. Now we have to draw the perpendiculars of the line joining this point to the nearby lattice points. This is the Wigner-Seeds cell in the reciprocal space of a graphene lattice. So these are the questions that have been asked from IISER Trivandrum. So this is the reciprocal lattice of graphene. I forgot to write A star and B star. This is A star and this is B star. Here also it is A star, B star.